Today we're going to talk about electrical potential energy, but to start off we're going to go back and talk about potential energy we're quite familiar with, and that is gravitational potential energy. So if you recall, we've got gravitational potential energy. So we've got a ball, it's up here at some height above the zero level, and we get to pick the zero level. We typically picked the lowest point to be the zero level, but we were able to choose that. And what we learned was that as this ball fell, its gravitational potential energy would go down. However, its kinetic energy would go up. Okay? Because its speed would increase, so the kinetic energy would go up, and the height would decrease, so the gravitational potential energy would go down, and mechanical energy would be conserved as long as we weren't worried about friction. Okay? And we use this equation. The gravitational potential energy was equal to the mass times the gravitational field times the height. We're going to relate this to electrical potential energy. So what we're going to do is we're going to create a capacitor here, and that's just two charged plates with opposite charges. Make the top plate positively charged and the bottom plate negatively charged. Now, we learned previously that electric field lines point away from positive charges. So in this case, our electrical field is going to be pointing downward. Okay, and we're trying to simulate up there, gravitational field always pointed downward, so we're going to go ahead and set this one up so that it's pointing downward for this example. Now, let's go ahead and place a positive charge in this electric field. So right here we've got a positive charge. Okay, what's going to happen to this charge? Well, the electric field is pointing down. It is a positive charge. So this positive charge is going to move downward. Well, that means it's got some kinetic energy. It's moving now, which by conservation of energy means that energy needed to be somewhere else before in some potential energy. And we call that potential energy the electrical potential energy. Okay? So we have a potential energy that we call the electrical potential energy, and that is going to decrease as this begins to move, okay? Because its kinetic energy is going to increase, just like okay? And this electrical potential energy, let's try to draw some connections here with our equation. Instead of the mass, it's not the mass of this electric charge that we're worried about, it's the actual charge, the magnitude of the charge. Okay, so we're going to have the charge there. We're not worried about the gravitational field, we're worried about the electrical field. Okay, and it's not a height because I drew this so that the electrical field lines would point down, but we could have rotated this. They could be pointing to the right, they could be pointing up, they could be pointing to the left at some angle. Okay, so it's not a height, all right, but it is a distance, so we're going to use a distance here. Now, in the equation up here, zero height could have been anywhere, okay? We weren't ever really worried about the actual potential energy. We were always worried about the change in potential energy, and we're still worried about the change of potential energy with electrical potential energy. So we're going to look at the change in potential energy, and that's going to be equal to the charge times the electric field times the change in its distance, okay? Now, there is one big difference between these two, and that is that this gets a negative sign in front of it, okay? The reason being, up here, gravitational potential energy is going to go down as the ball drops, okay? And that's because the height's going to decrease, all right? Down here, we need this potential energy to go down as the electrical charge picks up its speed as it moves, okay? So we need this negative in here because if we take a look at this, all right, let's look at the positive charge, okay? If it's a positive charge, then the Q would be a positive number. The electrical field is pointing down in this picture, so that would be a negative, okay? And the distance it would move downward. That would be a negative, okay? So we're going to get a negative times a positive times a negative times a negative, which would be overall a negative number. If you want the change in something, if it's negative, that means it was decreasing. Okay? So if you put a positive charge in there, the potential energy is going to decrease as it starts moving away. We want the same to be true. We want to also potential energy to go down if you put a negative charge in there. Because if you put a negative charge in here, it's still going to start moving. It's just going to move upwards. So let's go ahead and take a look at that. So if we use our equation, we'd have a negative. Then we have a negative charge. The electrical field in our picture is pointing downwards, so that would be negative. And the distance it's going to move now is upwards. That's the positive direction. Okay, well, negative times a negative times a negative times a positive is still a negative, which means the change in potential energy decreased. Okay, so there's one big difference, okay, and that's the negative. And the negative's in there to ensure that the potential energy decreases as the kinetic energy increases. Okay, this isn't the only equation that we have. We can take our equation, potential energy is equal to negative the charge times the electric field times the distance. Okay, and we can change it up a little bit. We take a look at this. The charge times the electrical field. That is equal to the electrical force. Well, the electrical force is also equal to Coulomb's constant times charge 1 times charge 2 divided by the distance between the charges squared. So I can take this and substitute it in for that. So then we can have the potential energy is equal to K Q1 Q2 over R squared. Now, this R is the distance between the two charges. This is a distance, so we're going to just change that D to an R. Notice these cancel out. Okay, and our electrical potential energy is equal to K Q1 Q2 over R. Notice, I dropped the negative. Okay, there's a reason for that. Okay, in our first equation, we could let the potential energy of 0 be 0 wherever we wanted, whatever spot we wanted. Here, we cannot. In this equation, if you look at it, the potential energy is going to get smaller and smaller the bigger this number gets. Okay, so as the distance between the charges approaches infinity, this approaches 0. Okay, so it kind of takes care of making sure that the potential energy decreases when it should. Okay, all by itself. So this equation does not have the negative in it. Let's go ahead and look at these. Electrical potential energy. Work is done to move a charge from point A to point B. Okay, this work is equal to the change in electric potential energy. The change in the potential energy is what we're really worried about. Similar to when we were talking about gravitational potential energy, we were worried about the change. We've got two equations, one if we know the electric field, the other if we have two charges. Okay? Things we need to remember, electric potential energy should be in joules, the charge should be in coulombs, electric field should be in newtons per coulomb, distance from 0 is in meters in the letter D, the distance between the two charges is R, and again, both of those are in meters. We should include the positive or negatives for the charges in both these equations. When we were doing the fields and the forces, we just looked at the directions later. This is a scalar. We're not worried about the direction here, which means we do need to include the negatives in our equations.